Hello. Good morning, everyone. I want to welcome you to another Multivariate statistic class. Like I said on Monday, there's not going to be any new assignment this week because I want to slow down, so that will give you opportunity to have a recap on what you've done before. So, I actually have two materials today to accomplish, but I'm going to, because of the feedback that I got from one of the students asking me to clarify this page because before moving to this page, I talk about ANOVA for regression. And of course, in the ANOVA for regression, I remember I talk about splitting the total sources of variation into various components where we're going to have variation explained by the model that we call sum of square regression and the unexplained variation. So what I'm going to say here, if you take a look at the column here, okay, that is a sum of squared. Now, um, the factors involved, if I add all of these together, that is sum of squared regression. The totality of that is a sum of square. So that is actually going to be, we're going to call that sum of square regression after adding that together. Okay. The sum of square regression is explained variation. And of course, this guy here is the sum of square error, the sum of square error. And of course, if I had the sum of square regression to sum of square error, I'm actually going to have the total sum of square. So I want to believe the person understand right now. So the sum of square regression here was actually broken down because we have, more than one variable, cylinder, the AM, CARB, all of that, okay? Except that here we broke down the sum of square regression into various components. So, and we have different type of sum of squared. We have type 1, type 2, type 3. So this is just to tell you, this is a type 3, okay? So it's like we're looking at the situation in terms of, we can only use this when we have categorical factors. I'm going to say that again. We can use this only when we have categorical predictor. You know, you know what this one mean? The degree of freedom that you're seeing here. It means we got 3 levels of cylinder, and that was why the degree of freedom is 2. Okay. The AM and the carb, that you see the degree of freedom to be 1, 1, actually mean there are 2 levels of each. So here, the p-value here will enable you to measure the effect of cylinder, okay, on the MPG. Okay, you want to see whether MPG is going to be the same at 3 levels of cylinder. You want to see whether MPG is going to be the same at 2 levels of AM. You want to see whether MPG is going to be the same at 2 levels of CARB. Okay, I believe the person that sent me question really understand the explanation. Okay, so I will quickly move to where we stop on Monday. Like I said, I got 2 materials today, but we are presently reviewing regression that has to do with one dependent variable. Understanding that, you'll be able to understand, the multivariate aspect. Okay, I remember before I've walked you through how to construct a confidence interval for the regression parameter when the variance is known. Okay, you can see a z-score. And of course, when the variance is unknown, you actually see a t-score. Okay, now what I want to work on, and of course, what you see here is actually the code, for the multiple linear regression in R, where you are looking at the effects of cylinder, effect of AM, effect of carb on the MPG. Okay. So, and let me tell you the difference between this and the one I showed you the other time. Please, I need you to pay attention. Right now here, I'm looking I'm looking at the effect of this cylinder, effect of AM, and effect of carb on the MPG. I'm actually running that as a multiple linear regression here. And that is why you can see how many levels of cylinder do you see? Two, because there are three levels of cylinder, right? Because of, in order not to fall into a dummy variable trap, when you have three levels of a categorical factor, we're only going to, the arrow will report two levels. And the other level is nested, is referenced in the intercept. Now you can see AM, you can actually see carb. Okay, so here is trying to say the AM is continuous and the carb is continuous. So I just wanted to take note of that. So here we are running a multiple linear regression, but in the one I showed you before, it is not a multiple linear regression we are running. We are running analysis of variance. Please pay attention. There's a difference between running a regression and running analysis of variance. I'm going back to that. Here, now take a look at this. Here, I'm running analysis of variance. Whenever I'm running analysis, that's why you see F and P of F. Because in analysis of variance, we use F-test. But before you can run analysis of variance, all the predators have to be categorical. To run analysis of variance, all predators, when I mean predator, I mean explanatory variables, have to be categorical. Okay? So I just wanted to see the difference. Okay. Now, I'm actually going to move to where we stopped the other time on Monday. Now, I wanted to start from here, and I need you to pay attention. Okay, give me 1 second. Yep, I wanted to start from here. I need you to pay attention. But before understanding this, I think I will first come here. Now, for instance, if I want to conduct a test that I show you on Monday, where I have H naught, okay, the null hypothesis is beta 1 equal to 0, okay, beta 2 equal to 0, okay, all the way to beta p equal to 0. Please pay attention. All the way to beta p equal to 0. And the alternative is saying at least 1 is not true. Okay? And the alternative is saying at least 1 is not true. Now, when H naught, when beta 1, beta 2 up to beta p equal to 0, that H naught is only supporting an intercept model. I'm going to say that again. When beta 1 is 0, beta 2 is 0, up to beta p is 0, the H naught supports intercept model. Why the alternative supports model with covariate. I'm going to say that again. When H naught, okay, support intercept model, the H naught here means model without covariate. Why the alternative hypothesis is model with covariate. If I really want to know what is the p-value to use in taking a decision, it's going to be this. That is the p-value I'm going to use in taking a decision. Can you see that? And that very p-value is the one that is associated with the F statistic here. Okay? But if I want to take a decision about individual predator in the model, then I'm going to use the p-value here. Okay? If I want to take a decision about the contribution of individual predator in the model, I'm actually going to use that p-value. But if I want to take a decision, so here we use a t-test. For the individual one, it is a t-test. Okay, for the individual one, it's a t-test. But for the general one, it is f-test. Please, I need you to pay attention as I want you to know the difference between f-test and t-test. The t-test will test the individual contribution of predator in the model, while the f-test will test the overall contribution, the adequacy of the overall model. Now, the bottom line is this. When I'm testing a model without covariate, with model with covariate, I use f-test. But what if in a situation where I want to compare two models, none of them is intercept model. Okay, I want to compare two models. One is simple, the other one is complicated. I'm going to say that again. I want to compare two models. One is simple, the other one is complicated. Why? What do I mean by one is simple? Maybe one has two predators and the complicated has more than two predators. That's what I mean. And what do we use in that regard? We don't use f-test. We use a nested f-test. And that is what I'm trying to investigate here. Please pay attention. Take a look at this. If you take a look at that, I'm testing between simple model and complicated model. And if I want to do that, I'm going to say simple model is a reduced model. 1 second. I'm going to call simple model a reduced model. Can you see here? You know, why is this one called a reduced model? Okay. Now, if you take a look at this one, this is a full model. Okay. A full model is a complicated. The reduced model is a simpler model. How do I test for that? Okay. Now, if I want to test for that, we actually need to adjust our F. We're not going to use f-test, but we're going to adjust that. But after adjusting for f, we're actually going to have a nested f. Now, what I'm trying to tell you now, okay, if I actually want to test, I'm going to use this. That's what I'm going to use. That is a nested, let me write that, nested f-test, nested. At times, we also call it partial f-test. So nested f-test. We use a nested f-test when we are comparing between simpler model and complicated model. And of course, this is the F distribution. Okay, when F is greater than that, that's a table value of F. When F is greater than that, we're actually going to reject H naught. Okay, I needed to pay attention to that. Okay, now the moment you understand what the formula now, if you really want to know what is the sum of square E, let me tell you this. The first one, this is the sum of square error for the reduced model. When I say reduced model, I mean for simpler model with fewer number of predators. This is the sum of square error for the full model, that is for the complicated model. And of course, this is the corresponding degree of freedom. We have degree of freedom for the reduced model, degree of freedom for the full model. Okay? I need you to pay attention. And all what I'm doing here is just to tell you, okay, this guy is the degree of freedom for the reduced. This guy is the degree of freedom for the full model. So when you talk about full model, the degree of freedom will be n minus p minus 1. When you talk about reduced model, the degree of freedom will be n minus q minus 1. Okay, please pay attention to that. Now, when you have that, okay, I'm still gonna show you how that is done in R. But the next on the line is, how do we test hypotheses that have to do with the linear combination of parameters? Okay, we have a parameter C. Okay, we have a constant C from C1 up to C plus 1, and the B is the regression parameters. And we may want to test hypotheses that, oh, the linear combination equal to B equal to a certain B, and the alternative is going to say, oh, it is not equal to that. And how are we going to test hypothesis about that? We can use a t-test. Okay, now if you take a look at the t-test, then this one is going to be the sample. If you take a look at that, because here, the B here is a population parameter, but here, what do you see? You see a B cap, right? That is the estimate. Don't forget your B cap. You remember how you get your B cap? X transpose X inverse. Inverse, you remember? X transpose Y. Okay? Now, the combination of the B cap, and don't forget the B cap that you have. You know, you have so many B0, B1, and so on like that. Then minus the B star here is an hypothesized value. The value you want to test. They're going to give you that value. You're going to plug that in. And what you see here is the standard error of this guy. I needed to pay attention now. This guy here is the standard error, of what? Of C transpose B cap. Okay, of C transpose B cap. What am I trying to say in essence? I'm trying to say in essence that I have an estimate. This is an estimate. It's like you have an estimate minus the hypothesized value. Okay, this is the estimate minus the hypothesized value divided by the standard error. This is the standard error, and that follow T distribution with n minus p degree of freedom. Now, that is for the linear, how to test hypothesis about the linear combination involving, the regression parameters. Now, the last on this particular page, on this particular lecture note is, we have constructed confidence interval about regression parameters. We have also learned how to construct a confidence interval. We've constructed confidence interval about regression parameter. We tested hypothesis about regression parameter. But can we also conduct inference on the variance? I'm going to say that again. So far, we've been testing hypothesis about regression parameter. We've also succeeded in constructing confidence interval about regression parameter, but can we also construct a confidence interval about the variance? Because at times the focus may be on estimating variance. I'm going to say that again. The focus may be on estimating variance. You remember the other time when I was using the method of maximum likelihood. From the method of maximum likelihood, we can derive maximum likelihood estimator for the regression parameter. We can also do the same for the variance. I told you the other time we can differentiate with respect to sigma squared. Now, when we want to estimate the sigma square, I think I remember I gave you two ways. We have a maximum likelihood estimation for sigma squared, and we have what I call the sample estimate of the sigma squared. But all of that will only give a single value that could be wrong or right. We call that a point estimate. We cannot rely on point estimate in statistics because of that. Can we have a way to construct the confidence interval for it? This is the derivation, but I'm going to show you the final. Now, I need you to pay attention. Take a look at this. That formula is used to construct a confidence interval for the variance. Instead of us to have a single value for variance, then we're going to have variance in an interval. The true value of the variance will be in an interval where we can have a lower bound, we can have an upper bound. And of course, the sigma cap square that you are seeing will be the estimate of the variance. And a follow chi-square distribution. It means we're going to check value in the chi-square. So take a look at that. So that is the formula. I'm actually going to move right now. Now, the last but not the least, we want to talk about predicting observation, new observation. But when we're talking about prediction, there are two types of prediction. We have average, we have prediction for average, we have prediction for individual. I'm going to say that again. There are two types of prediction. Prediction for average. When I say prediction for average, then I want to do prediction at group level, because average is involved. When I say prediction for individual, I only mean individual. Okay, now we're going to have a point estimate of prediction for individual and a point estimate for average. We're also going to have interval estimate for prediction for individual and interval estimate for prediction for average. But you know what I want to walk us through? Let's first look at the average. And that is what I mean here. Take a look at that. Whenever you hear expected value of response, then it means I actually want to make a prediction for average expected value of the response. Now, if I want to do that, I'm going to go back to our model for prediction. You remember the model for prediction in regression? It is that. So which means, I already obtained my B cap, right? After obtaining my B cap, if I know the values of X, then I can predict Y. Does that make sense? Okay. But you know what this guy is going to give me? What I circle is going to give me? It's only going to give me a point estimate of prediction that may not be reliable. Does that make sense? Now, what do I need to do? If I want to create an interval estimate for prediction, now let me tell you this, in statistical analysis, we normally prefer interval estimate to point estimate. Why? Because a point estimate could be misleading. It could be too low or it could be too high. Does that make sense? Now, if I need an interval estimate for this prediction, then I need a standard error for this prediction. And now am I going to get a standard error for this prediction? Then I need a variance. Because when I get the variance of the prediction, the square root of the variance for the prediction will be the standard error. Now pay attention. The variance of the prediction is this guy. That is the variance of prediction. Okay, if you remember what we did on Monday, please pay attention. Okay, if you remember what we did on Monday, I'm seeking the variance for this guy, right? Now take a look at this. That means variance of that, right? Now, what is a constant in the parentheses? The constant is X. I told you S is fixed, right? When x come out of the when the constant come out inside the variance in scalar, it becomes a square, right? But how do you write square the matrix? We're going to write the x here and the transpose here. Can you see that? And the variance we attract the B cap. But on Monday, do you know I show you something on Monday? What is the, I derived the variance of a B cap. What was the variance of the B cap that I actually show on Monday? The variance, let me remind you, the variance of the B cap that I derived on Monday was sigma squared x transpose x inverse. You remember I derived that on Monday. The variance of the B cap. That was what I put here. Now, you now see that now, how we derive that now? That is the variance of the prediction. Variance of the prediction. Why am I interested in the variance of the prediction? Because before I can construct interval, a confidence interval on the prediction, I need the variance of the prediction. In fact, not even the variance that I need, the standard error of the prediction. But I can't get to standard error without passing through the variance. Now, if the sigma square here, if the sigma squared here, if the sigma square here is unknown, then we can use the one, we can estimate it from the data. You see sigma cap squared? That is for situation where sigma squared, the population variance is unknown. Okay, now that is that. Now, let me tell you this. If I have a prediction, if I want to perform statistical inference on a prediction, statistical inference means construct a confidence interval I just show you. Another one means, can you test hypothesis about prediction? Okay. Now, the prediction I'm talking about is not for individual, for average. Now here, this is going to be the null hypothesis. This is going to be the alternative. This is trying to say, the average prediction is a value, y star h. An alternative is saying it is not. But let me tell you this. Whether you want to construct a confidence interval or you want to test hypothesis, we need the standard error. And I told you the other time. Now, what is happening here. Please pay attention. I'm going to conduct a t-test. Okay. And do you know what you have in the denominator? What you have in the denominator is the standard error of the prediction, which is the square root. That guy that you have in the denominator here is, I'm going to show you where it is here. It is the square root of, it's going to be the square root of this guy. That guy that you have in the denominator of the test is the square root of this guy. This guy is the variance. Can you see something? Sigma squared y bar h. That is the variance, right? That is the variance of average prediction. Okay. The square root of that becomes the standard error. If I want to construct a confidence interval, I'm going to use that standard error. If I also want to test hypothesis, I'm going to use it. And that is it. That is exactly what I'm referring to here. That is what I'm referring to here. Now, let me now write the confidence interval formula out so that you're going to see, oh my God, look at this guy and look at this guy. In the two formula, what do you see? There's a standard error. The standard error is sigma cap y bar h. That standard error that you see in the denominator of the t-test and the standard error that you see that is multiplying t multiplier, that standard error is the square root. It is the square root of let me do this. I'm gonna clean up this now and I'm gonna show you so that you'll be able to see the connection. Now pay attention now. Pay attention now. The standard error here and the one here. is the square root of this guy. The square root of that guy. Is there any question on that? So whether I want to construct interval or I want to test hypothesis about prediction, I need the standard error of prediction. And how am I going to get the standard error of that? Then I find the square root of that guy. Okay, now that is for the average. Like I said, average. Okay, now I want to move on to the individual. I just finished the average right now, and I'm going to have a recap. When we are talking about prediction, prediction comes in two forms: one for average, one for individual. The one I just completed is the one for average. Now, the one for average, I give you the formula to figure out the point estimate of prediction for average, and I also give you the interval estimate for prediction for average. And not only that, I give you the formula to conduct an hypothesis testing. But you know what I want to do now? I'm not interested in the average anymore. I want to talk about individual. Prediction for individual. Prediction for one person. Now, in the prediction, and that was why I said, I said I want to estimate observed value of response for a given predictor score, not average score now. Now, take a look at this. I need you to pay attention. Pay attention. Do you know what? Whether I'm talking about individual prediction or I'm talking about average prediction, the point estimate is the same. Do you see the same formula for point estimate? Whether for individual prediction or for average prediction, the point estimate is the same. But do you know where the difference lies? Where the difference lies is in the variance. The variance of prediction for average is different from the variance of prediction for individual. Does that make sense now? The variance of prediction for average is different from the variance of prediction for individual. Okay. Now, why do we have it that way? Because I can decompose the variance. You can see here. What do you see? Sigma square y-ish. Before, what do you see? Before, what you saw before was sigma square y bar-ish. This one is for the mean prediction. But if you take a look at that guy now, it doesn't have any bar. That is for the individual. Now, the one for individual can be broken down into, oh my God, look at that. The one for individual can be broken down into the variance for the mean that we just talked about and sigma squared. Now, based on the variance, can somebody tell me, based on the variance, which one do you think we have a smaller variance between individual prediction and average prediction? Can somebody tell me? Which one we have a smaller variance? Go ahead. Average. And that justify the reason why in statistics we prefer predicting at the average level. Does that make sense? And that's why you're going to hear average effect, average this, average that, because the variance associated with that will be smaller than the other one. Okay, does that make sense now? Now, how do we do this in R? Please pay attention. I'm going to show you how we do that in R. But before going to how we do that in R, just like what we did the other time, we can test hypothesis about individual, and testing hypothesis about the individual. Pay attention. What I'm going to have here is still going to be the same formula, except that here, this guy, that standard deviation is not going to be the same as the standard deviation for the average. The same thing here. But how are you going to know? I want to show you numerically. I want to show you numerically. Okay? And you're actually going to see what I'm talking about. Let's come to this in R. Now I need you to pay attention. Do you know why I'm spending a lot of time on the univariate? I'm spending a lot of time on univariate. The moment you understand univariate or regression, then you will be able to understand multivariate regression. And that's why I'm trying to slow down. Now, I need you to pay attention now. I want to show you the code in R. I want to show you that if whether you are talking about individual prediction or average prediction, the point estimate will be the same. I'm going to say that again. Whether you are talking about individual prediction or average prediction, the point estimate will be the same. But let me tell you this. Whenever you hear, take a look at this. In R, when you hear something like this, confidence interval, prediction interval, I want to distinguish that whenever you hear confidence interval, you know what we mean? Whenever you hear confidence interval, we mean interval for average prediction. I'm going to say that again. Whenever you hear confidence interval for prediction, then we mean interval for average prediction. Whenever you hear prediction interval, then we mean interval for individual prediction. Does that make sense? Now, what is the code? I need you to pay attention now. I need you to pay attention now. Now, look at what I'm doing here. When you hear confidence interval, I want to have an interval for what? For average prediction. Now, this is what happened. We're looking at the effects. Don't forget the example we're treating. We're looking at the effect of three predictors on the response. What are the predictors? We have cylinder, and we got three levels of cylinder, and AM, maybe transmission, continuous, and carbon. Okay. Now, if I have new information about I know I have information about the predator. Now, the information I have about the predator is, take a look at this. Out of the three level of cylinder, maybe I have the information that is cylinder 6. Okay, maybe I know, oh, this is a cylinder with 6 well, I mean, this is an engine with 6 cylinder, and my AM equal to 1 and this guy equal to 4. If you take a look at this, it's more or less like in a multiple linear regression. I know the values of x1, I know the values of x2, and I know the values of x3. But what I want to do, I want to make a prediction for the MPG, the response variable, but the prediction I want to make is the average. Then I'm actually going to write, look at the code in R. Predict, MOD, of course, MOD is the model that you fitted initially, right? MOD, new data, of course, your new data, you know the values of x1, x2, and x3. Then in the interval, you're actually going to write confidence. You will write confidence for interval estimate for prediction that has to do with the average. What is the difference? Okay, from the one that has to do with individual. The one that has to do with individual, I'm still using the same data set, but look at the difference. The one for the average, I actually write confidence for interval. The one for the individual, then I wrote prediction. Look at the difference. Now, I told you the other time, because I'm using this guy for both, because I'm using this guy, for both, then look at this. Point estimate for average is going to be the same as the point estimate for individual. Do you see that? The two are the same. The point estimate for average is going to be the same as the point estimate for individual, but you know what? Because the variances are not the same, then one will have a wider interval than the other. Does that make sense? Now, the average has a lower variance. I need you to compare this now in terms of range. Give me 1 second. In terms of range, I need you to compare this guy with this guy. Which one has a wider interval? You can say the one with a wider interval is a prediction interval. Can you see that? It has a wider interval because the standard error is large. The standard error is large because the variance is large. And this is the reason why in statistical analysis, whenever we want to make a prediction, okay, we like making our prediction around the average, not individual. Because individual one, in terms of what you're seeing right now, the individual one is going to have a wider range, while the average one is going to be narrower. Okay, this is the end of this material. Actually, I want to I'm gonna stop my writing now. I'm gonna say something. Okay, I now want to welcome you officially into, now that you understand. But let me tell you something. Before you can come to this material that I want to start now, you have to make sure you have an extensive review of the material we just completed. Because we're actually going to rely exclusively on the material we just completed. Now, the material we just completed, I will walk you through. We're looking at the effects of some selected predictors on one response variable, but right now we want to move to multiple response variable. Because of that, I want to welcome you to multivariate linear regression. Now, I'll quickly run over this because, like I said, we're actually going to rely on the knowledge that we've acquired in the material we just completed, the univariate version. Now, this is the multivariate. Now, when you take a look at it, please pay attention to the model specification. Oh my God. In the model specification, can you see K? Can you see K? That very K implies that we have more than one dependent variable. Does that make sense? We have K, okay? In the Y, we have K in the B0. The K in the B0 means I'm not going to have just one intercept. If I have two response variable, I'm going to have two intercepts. If I have three dependent variable, I have three intercept. If I have K number of dependent variable, I'm actually going to have K number of intercept. Not only that, I'm also going to have for the slope. Now, do you understand that specification? Okay. Now, the same thing will be applicable. Now, you're actually going to see something here. There's a particular component that is not affected by K. Oh my God. It is, of course, that is not affected by K. Okay. Now, the error too also going to be affected by K. Okay. The number. So that is the model specification. And when I ask you to state the model, stating a model, specifying a model is to define what each term represents. Please pay attention. What do you see now? What each term represent? Okay, and you can see there's a special definition for the error. Look at the error now. You see that E1, EI1 up to EIM, IID, normally then with 0M and variance covariance, which is a multivariate Gaussian error vector. Now, the only difference is just like we are actually extending this to multiple dependent variables. Now, and that is why if you see m greater than 1, m here, m represent the number of dependent variable. So which means this is applicable to situation where the number of dependent variable is more than 1. And of course, we have p greater than 1 means I have more than one explanatory variable. Now I have more than one explanatory variable. I also have more than one predator. I need to pay attention. And that's why you see when you see BJK, okay, the BJK, J start from 1 to P plus 1. Okay, you know why P plus 1, right? The intercept is being added to the number of parameters. And K start from 1 to M, which is going to be the number of dependent variables. I just wanted to take note of that. Now, the variable now, do you know the meaning of this one? Please pay attention. If you don't understand, ask me a question. You have the right to ask me a question. You pay for this service. If you don't understand, ask me a question. You know what Y1 means? Y1 is a vector on its own. Y1 is just like, oh, one response that have so many values is a vector. Y2 is also a vector up to Ym. Do you see that? And you have X1 up to XP. Please pay attention. Okay? Pay attention. Now I'm moving. Now, whenever we specify model within a statistical framework, we normally, also state assumptions. What make a model to be great is when all assumptions are met. Now, what if I ask you in exam, what are the assumptions of multivariate linear regression? I'm expecting you to state all this. You can see, okay? You can see all this. These are the assumptions. Then the homogeneity of variance for each response. Okay? These are the assumptions. Okay? Now I'm actually going to move. Now we want to come to how to write it in matrix form. What of an exam? I said, write a multivariate linear regression model, okay, in matrix form. Okay, this is what you're going to write. You can see an uppercase Y, an uppercase X, and I'm writing an uppercase B. But when I was dealing with one response variable, okay, I did not write uppercase B, I write a lowercase b. Okay, and if you look at the E error here, I did not write an uppercase E for one dependent variable, but right now I'm writing that. Now, whenever you state a model, look at the definition. Do you see why? Please, this is the way I want it to be reading. Look at this. Do you know what you're telling me? Oh, I'm not only having just one Y, I have M numbers of Y. Each of this is a vector. Can you see that? Okay. And you can see the dimension here. N by M. Why is it N by M? Because each Y, there is the number of observation is N. Then you have M numbers of Y. That's why you see N by M. Okay. Now the X remain the same, but look at B. Please pay attention. Do you know what B1 means? For instance, if I'm talking about a particular BK, maybe a particular one, this is a particular one. Do you see that? Do you know if I let K to be 1, I'm going to get for B1, I'm going to get for B2, I'm going to get for B3, okay, and so on like that. Don't forget, because a multiple dependent variable is involved, we expect multiple slope, okay? Not only multiple slope, multiple intercept. Now, this is the error now, okay? This is the error now, okay? Now, oh my God, how do we write it? This in matrix form. This is where I'm actually going to stop. Take a look at this guy here. This is for one dependent variable. For two and so on, this is for M. dependent variable. Look at that. Okay. Now, what do you see? The design matrix X does not change. Design matrix X will remain the same. Oh my God, look at this guy. Look at this guy. I told you the number of intercepts you're going to have is going to be M. Look at the numbers of intercept here. They're going to be M numbers of intercepts, M numbers of B1, M numbers of B2, up to M numbers of that. The same thing with the error. This is where I'm going to stop. We'll continue from here on Friday. Now, let me tell you this before you go. I will release midterm 2 practice question on Friday, but let me narrow your reading. The midterm 2 will not cover multivariate, whatever we're doing in multivariate or regression, but it's actually going to cover what we've done, I believe, multivariate normal distribution, and the chapter we just finished. Does that make sense? That is what midterm 2 will cover. So midterm 2 will not cover anything multivariate. Will not cover multivariate linear regression that we've been doing, but it's actually going to cover multivariate normal distribution and vector means, inference on vector means, whether for one population, for two population, or for three population, okay, or for more than that. So that's what it's going to cover. But on Friday, I'm actually going to release the practice question for the midterm too. And I'm also going to go over that next week before the exam, just like the way we did for midterm 1. Make sure you all stay safe and have a lovely day. If you have not picked your exam document before, I have it here. You can come and pick them now.